There is a class of world that does not rise over any sunrise. It has no parent star, no familiar orbit, and no permanent place in a planetary system. It drifts through the darkness between stars, carrying an atmosphere that may glow, rain, and even form clouds, while the universe around it remains almost completely black. These are rogue planets, and the James Webb Space Telescope is giving astronomers a new way to find them. Not by watching them cross a bright star, but by detecting the faint infrared warmth they release into space. In the next 10 minutes, we will follow that heat, explore how a planet can become lost, and ask whether the darkest worlds in the galaxy could still have surprisingly complex weather. A planet is called rogue when it travels through the galaxy without being gravitationally bound to a star. Some may have formed normally in a young planetary system and then been thrown out by violent encounters with larger planets. Others may have formed alone, inside collapsing clouds of gas, following a process more similar to star formation than to the birth of Earth. The distinction matters because a free-floating planet is not simply a planet with its lights turned off. Its entire environment changes when the star disappears. There is no daylight side and night side. There is no yearly cycle caused by an orbit. The energy that shapes the atmosphere must come from the planet itself, from slow gravitational contraction, radioactive elements, or the leftover heat of formation. That heat is invisible to human eyes, but it is not invisible to Webb. The telescope observes infrared wavelengths, the region of the spectrum where cool objects radiate most strongly. A rogue planet may be too faint to see in ordinary visible light, yet still stand out as a warm ember against the cold background of space. The first challenge is distance. Even the nearest stellar neighborhoods are enormous, and a planet without a star has no bright beacon to announce where it is. Astronomers search young clusters, places where hundreds or thousands of objects formed at roughly the same time. A young planet is brighter in infrared because it has not yet had billions of years to cool. In these clusters, Webb can separate tiny points of light and measure their colors. A planet's infrared spectrum can reveal water vapor, methane, carbon monoxide, and clouds made from silicate minerals. The result is not a photograph of a world with oceans and continents. It is more like a chemical fingerprint, assembled from light that began its journey before modern civilization existed. Some of the most intriguing candidates are not Earth-sized. They are objects with masses comparable to Jupiter, but with temperatures, atmospheres, and formation histories that may overlap with the smallest brown dwarfs. Brown dwarfs are sometimes called failed stars because they are too small to sustain the hydrogen fusion that powers stars. Rogue planets and brown dwarfs occupy a blurred boundary where nature refuses to respect our categories. This is one reason the discoveries are so important. Planet formation may not be a single recipe. The familiar picture says a young star is surrounded by a disk of dust and gas. Small grains collide, become rocks, become planetesimals, and eventually grow into planets. But if isolated planetary mass objects can form directly from collapsing gas, then the galaxy may produce worlds in more than one way. There is also the question of how many rogue planets exist. Estimates vary widely because these objects are so difficult to detect. The Milky Way may contain billions of them, perhaps even numbers comparable to the stars themselves. Every estimate depends on which populations we can see and which remain hidden below the sensitivity of our instruments. A free-floating planet can also become a natural laboratory for atmospheric physics. On a starbound planet, sunlight often dominates the upper atmosphere. On a rogue world, internal heat may drive circulation from below. Warm material can rise, cool, condense, and fall again in a cycle that has no daylight component at all. At temperatures of several hundred degrees, strange clouds may form from substances that would be rocks on Earth. Tiny grains of silicate can be carried through the atmosphere like dust. Iron-bearing droplets may condense deeper down. Methane and water can change relative abundance as layers rise and sink. The sky of a rogue planet could be dark to the eye, yet violently active in infrared. Webb's instruments can detect these molecules because each one absorbs and emits light at characteristic wavelengths. As the telescope collects photons, a spectrum develops. A dip at one wavelength or a broad emission feature at another can tell researchers what is floating above the clouds, how hot the atmosphere is, and which layers they are seeing. But spectra are not simple labels. A cloud can hide the molecules beneath it. Temperature and chemistry can imitate one another. Dust can reshape the entire signal. Astronomers must compare observations with sophisticated atmospheric models, testing thousands of possible combinations until the physical story is consistent with the data. The best observations may come when multiple telescopes work together. Webb measures infrared chemistry. Ground-based observatories can track motion across the sky. Future surveys may use gravitational microlensing, a technique in which a foreground object briefly magnifies the light of a background star. A rogue planet can create a short, distinctive flash as it passes in front of the alignment. Microlensing is powerful because it does not require the planet to emit much light. It can reveal cold, dark objects that would be nearly impossible to photograph. The disadvantage is that the event may last only hours or days, and once the alignment is gone, the planet may disappear from view again. If the galaxy is filled with these invisible wanderers, they could affect planetary systems in ways we are only beginning to understand. A rogue planet passing near a star could disturb the orbits of comets and distant planets. In a young system, gravitational encounters may eject worlds outward, transforming a compact family of planets into a sparse and chaotic one. Our own solar system preserves clues that something violent happened long ago. The tilted orbits of some distant objects, the structure of the Kuiper belt, and the presence of planets with very different compositions all reflect a complicated history. That does not prove a rogue planet passed through, but it reminds us that planetary systems are not quiet clockwork mechanisms. They are gravitational experiments that can rearrange themselves. Could a rogue planet support life? The answer is uncertain, and the conditions would be extreme. Without starlight, surface oceans would tend to freeze, and photosynthesis would have no obvious energy source. Yet a thick atmosphere could insulate the surface, while tidal heating or radioactive decay might keep a subsurface ocean liquid beneath an icy crust. In our solar system, moons such as Europa and Enceladus demonstrate that liquid water can exist away from the sun when internal energy is available. A free-floating planet with enough heat and insulation might preserve a similar hidden environment. Any life there would likely depend on chemistry, not sunlight, perhaps drawing energy from reactions between water, minerals, and gases. This possibility should be treated carefully. Detecting water vapor does not mean detecting life, and finding organic molecules does not establish biology. The scientific value of rogue planets is that they let us test the limits of habitability, separating the requirements for life from the familiar accident of living on a temperate planet beside a star. There is another mystery: how long can these worlds remain warm? A young rogue planet may glow strongly, but its heat fades over time. The atmosphere becomes colder, clouds change, and the object moves toward a state where only the deepest infrared observations can reveal it. The galaxy could contain ancient planetary remnants that are almost as cold as interstellar space. A future generation of observatories may find them through their influence rather than their light. A passing object can bend starlight, alter the motion of a visible star, or leave a subtle signature in the distribution of distant icy bodies. Each technique sees a different piece of the population, and together they may reveal how common these wandering worlds truly are. For now, Webb is opening the door by showing that planetary mass objects in darkness are not featureless. They have atmospheres with layers, clouds, winds, and chemistry. They can occupy the border between planets and stars, challenging a definition that once seemed obvious. The deeper lesson is about how we search for worlds. For centuries, the most natural assumption was that a planet belongs to a star the way a moon belongs to a planet. Rogue planets break that visual connection. They show that a world can exist without a sunrise, a calendar, or a warm central star to make it easy to find. Somewhere in the Milky Way, an unlit planet may be crossing a cloud of interstellar dust. Somewhere else, a young world may still be collapsing under its own gravity, heating from the inside as its atmosphere takes shape. And far away, an ancient frozen planet may be drifting through the galaxy, carrying a history written only in faint infrared light. When Webb catches that light, it is not merely finding a missing planet. It is revealing a hidden population of worlds and forcing us to expand the meaning of a planetary system. The universe may be filled not only with planets that circle stars, but with planets that travel alone, dark, cold, and yet still alive with physics. And that may be the most surprising discovery of all: darkness is not the absence of a world. Sometimes, it is the only place where the world's true nature can be seen.